You know that feeling, don't you? You're cruising along on a big JavaScript project, everything seems stable, and then out of nowhere, a baffling bug decides to crash your production environment.
Yeah.
It's like finding a leak in your roof only after the rain has already flooded the living room, or maybe you try to scale, and that once nimble code base starts to feel less like a tool and more like a wild beast you're desperately trying to tame.
It's a tale as old as modern web development, really. JavaScript, it was born for quick, interactive web pages, but it's evolved into the foundation for these colossal applications. Millions of lines of code sometimes.
Right?
And with that scale, its dynamic nature, the very thing that made it so flexible, can become a bit of a liability.
Yeah, I can see that.
Those quirky behaviors, like console.log4,
Yeah.
producing infinity.
Yeah.
Syntactically valid, sure, but almost always a programming mistake.
A mistake you don't find until it's running.
Exactly, until runtime. We've all seen that infamous could not read property foo of undefined error pop up only after deployment. It's maddening.
Absolutely. Trying to maintain and scale those sprawling JavaScript code bases often leads to unexpected crashes and, well, just an explosion of bugs, turning development into a constant firefight.
It really can't feel that way.
But what if there was a way to truly rein in that complexity? Today we're taking a deep dive into TypeScript. Now, you might have heard it initially presented a steep learning curve for some people. Kind of broke some brains was a phrase I heard.
Oh, yeah, that sounds about right for the initial shock sometimes.
But it also consistently promises to equip you with genuine superpowers.
That's right. Our mission in this deep dive is to unpack exactly what TypeScript is, why it's become such an indispensable tool for developers, and, how it truly empowers you to build more robust, scalable, and maintainable applications.
We'll explore its core features, look at a practical, quick setup, discuss its seamless integration with popular frameworks, and maybe uncover some of the best practices that can transform coding from a headache into something, dare I say, genuinely enjoyable.
Hopefully, that's the goal.
Get ready for some profound aha moments and maybe some surprising facts that will make you feel incredibly well-informed and ready to tackle even the most complex coding challenges with newfound confidence.
Let's do it.
So let's unpack this and start with the core question. Why TypeScript? Why do we even need it when we already have JavaScript?
Well, as you hinted, JavaScript's incredible journey from a simple scripting language to the backbone of complex applications has really brought its dynamic nature into sharp focus. Because it's so flexible, many errors, especially those type-related ones, aren't detected until the code actually runs, often in production.
Right, the runtime surprises.
That's the root cause of those frustrating runtime bugs, yeah.
And as you mentioned earlier, some of those JavaScript behaviors are certainly...
It's interesting.
That console.log4 giving infinity is a perfect example of something that's technically legal but almost never what you actually intended. It's like a silent trap waiting to spring.
Precisely. And that's exactly where TypeScript steps in. It acts as a static type checker.
Okay, static type checker. What does that mean practically?
At its core, TypeScript is a typed superset of JavaScript that ultimately compiles down to plain JavaScript. So what it does is introduce a set of rules about how different kinds of values can be used.
Rules?
Yeah, rules about types. The fundamental shift here is that TypeScript performs static checking. It proactively detects errors in your code before execution at compile time.
So instead of discovering that dreaded could not read property foo of undefined after your code is deployed and users are hitting it, TypeScript helps you catch that bug while you're still writing the code. That sounds like a monumental leap forward.
It absolutely is.
Yeah.
This compile time error detection prevents a vast array of type-related bugs, making your software inherently more robust.
Yeah.
You're not just writing code, you're building with these built-in safeguards.
Okay.
And here's where it gets really interesting, I think. TypeScript never changes the runtime behavior of your JavaScript code. Never. Once compiled, all the type information is erased, meaning the type system itself has no bearing on how your program works when it runs.
Oh, okay.
So if you transition existing JavaScript code to TypeScript, it's guaranteed to run the exact same way. It's like having a really powerful spell checker and grammar assistant for your code that then removes all its notes before the final document is published.
That type erasure is a critical distinction. It means TypeScript is purely a developer tool, right? Not something that changes how your program actually executes in the browser or node.
Exactly right. It's all about the development process.
But I've heard some developers argue that adding types just means more boilerplate code, or maybe it slows down development initially. How do you respond to that perception?
Yeah, it's a common initial concern, I get that.
Right.
But the reality is often the opposite. While there's, sure, an initial investment in defining types.
A bit of upfront work.
A bit, yeah. But that upfront effort pays dividends by preventing far more complex and time-consuming runtime bugs down the line. The increased clarity and the powerful tooling TypeScript enables actually accelerate development in the long run, especially for larger projects.
So.
It transforms your IDE, your code editor, from just a text editor into a real-time knowledge graph of your application. It understands your code structure deeply.
That's a compelling promise.
Right.
So given these benefits and that powerful shift to compile time checking, what's genuinely driving TypeScript's explosive adoption? I mean, we see it everywhere now across so many major tech companies and projects.
There are several key drivers, I think. First, it profoundly enhances code quality. Static typing and things like interfaces compel you to think about your application's data structure and contracts right from the very beginning.
So better planning.
Better planning, which leads to superior architectural decisions in code that's far more maintainable and predictable. Second, it drastically elevates the developer experience, or DX as people call it.
DX, right.
Modern IDEs, like VS Code or WebStorm, will leverage TypeScript's type definitions to provide an incredibly rich environment. We're talking intelligent code completion that actually understands your code.
Not just guessing based on text.
Exactly. Powerful refactoring tools, real-time signature help as you type function calls, and these inline hints that proactively flag potential issues.
So it's more than just basic autocompletion. It's like having a highly intelligent co-pilot constantly scanning your work for inconsistencies.
That's a great way to put it. Yeah, a co-pilot. And beyond that, TypeScript offers, well, unparalleled scalability.
Scalability, how so?
It's trusted by tech giants like Google, Microsoft, Amazon, Apple. They use it for their most critical applications. That's a true testament to its enterprise readiness, wouldn't you say?
Definitely signals trust.
And because it's a superset, you don't need to rewrite existing JavaScript code to start using it. It integrates seamlessly, allowing for gradual adoption.
Which is huge for existing projects.
Massive. Plus, its popularity is also massively boosted by its deep integration with leading frameworks. It's the very backbone of Angular, as you probably know.
Right, Angular's built on it.
And it significantly improves type safety and the developer experience within React and Vue.js projects, too. What's more, Node.js now officially supports TypeScript by default, signaling its strong position in backend development as well.
Wow, okay. That's a powerful case for the why. So if TypeScript offers this incredible promise of taming complexity and preventing bugs, how do we actually bring it into our own projects? Let's maybe roll up our sleeves and look at the practical steps to getting started.
Sure. Getting started with TypeScript leverages the Node.js and NPM tools you're likely already familiar with. So you'll need Node.js installed, preferably the latest LTS version,
Okay.
and a package manager like NPM or Yarn. Most projects begin by initializing a new Node.js project, typically with NPM init-y. That just sets up your package.json file.
And that package.json file is where all your project's dependencies live, right? Makes it simple to manage everything.
Precisely. It tracks everything. Next, you need the TypeScript compiler itself.
TSC. Okay.
It's available as an NPM package, and you can install it either globally on your system or, more commonly, locally within your project using npm install save dev TypeScript.
As a dev dependency.
As a dev dependency, exactly. You can quickly verify your installation by running TSC version.
Got it.
Now, the crucial piece for any TypeScript project is the tsconfig.json file.
tsconfig.json, what does that do?
This file tells the TypeScript compiler where the root of your project is and how to configure its behavior. All the compiler options live there. You typically generate a default one with TSC in it.
Okay, so TSC-init gives you that config file. Once that's in place, how do you actually transform a TypeScript file, say mycode.ts, into runnable JavaScript?
It's quite simple, actually. If you have a TypeScript file like helloworld.ps, you just run tsc helloworld.ts into your terminal.
And that generates...
It will generate a helloworld.js JavaScript file right next to it, by default. The compiler is highly configurable through various flags in the tsconfig.json or on the command line. For instance, Watch will automatically recompile your files whenever you make changes.
Oh, handy.
Very handy during development. Or no implicit entity will disallow the compiler from inferring the any type which encourages much stricter typing from the outset.
Right, forces you to be explicit.
Yep.
Okay, but many modern web projects use sophisticated build tools, don't they? How does TypeScript fit into a workflow with something like, say, rollup.js?
Yeah, good question. For bundling and building complex TypeScript applications, tools like rollup.js are indeed indispensable. There's a great plugin at Rollup Plugin TypeScript that provides seamless integration.
Okay.
You'd configure your rollup.config.js file to import this plugin, specify your input files, typically something like srsindex.tss, and define your output directory and format.
And just add the plugin to the plugins array.
Yep, go TypeScript in its plugins array. What's fascinating here is that you can override specific TypeScript compiler options directly within the Rollup plugin configuration.
Oh, really?
Yeah, for instance, you could pass TypeScript target.esive.
Hmm.
These plugin options take precedence over what's defined in your tsconfig.json, giving you granular control for different build targets, like maybe an older browser build versus a modern one.
That's incredibly flexible for specific build scenarios. Is there anything tricky to watch out for, especially if you're using JSX, like with React?
Yes, that's a good point. A small note. If you're preserving JSX output, meaning you set jsx.preserve in your compiler options, this TypeScript plugin alone might not be sufficient. It could result in an error, unexpected token. You'd typically need another plugin, like at Rollup Plugin Babel, to handle that final JSX transformation into JavaScript function calls.
Okay, so an extra step for JSX preservation. Got
Yes.
it. We've covered the practical setup. Now let's talk about the foundational elements, the very building blocks that make TypeScript's type system so robust.
Right. The foundation really begins with explicit types. You explicitly define the types for variables, function parameters, and return types.
Like saying let name string.
Exactly. Let username string, John. That instantly prevents you from later accidentally assigning, say, a number to username. It catches that error at development time, not runtime.
Which is the whole point.
Which is the whole point. Then we have interfaces. Interfaces are essentially structural contracts.
Contracts.
Yeah, they define the precise shape of objects by specifying property types and method signatures. This ensures consistent data structures throughout your application and significantly enhances code clarity. They also support optional properties using a question mark or read-only properties for even finer control.
So interfaces enforce a consistent structure for your data, like a blueprint for objects, but without adding any runtime overhead because of that type erasure.
Precisely. They exist only at compile time to help you. And what about classes? TypeScript is often lauded for bringing more, let's say, traditional object-oriented programming features to JavaScript.
Right, class.
TypeScript truly embraces OOP. A class acts as a blueprint for creating objects, encapsulating both properties, the data, and methods, the behavior. It fully supports concepts like inheritance, extends, and access modifiers such as public, private, protected, much like you'd find in languages like Java or C#.
So you get proper encapsulation.
They get proper encapsulation and clear code organization, especially for complex object models.
And functions are, of course, a core part of JavaScript. How does TypeScript enhance them? What does it add?
TypeScript provides powerful ways to describe functions. You define parameter types, obviously specify return types, and you can even handle optional parameters using a question mark, like X number.
Okay.
It also supports something called function overloads.
Overloads.
Yeah, this allows you to specify functions that can be called in different ways, maybe with varying argument counts or types, all while maintaining type safety. It lets you define multiple signatures for the same function name. And this raises an important question. What if a variable needs to hold more than one type? What if something could be a number or a string?
Right, that happens all the time.
That's where union types come in.
Yeah.
They allow a variable to hold values of multiple specified types. You use the pipe symbol, for instance, function printed, print number string. Now, I can safely be either a number or a string.
That's incredibly flexible. And speaking of types, a common point of discussion and sometimes confusion is the distinction between type aliases and interface declarations. Can you clarify that for us and maybe offer some guidance on when to use which?
Ah, yes, type versus interface. This is indeed a frequent and important topic. Type aliases are incredibly flexible. They can express unions, map types, conditional types, essentially any kind of type you can imagine. You can give a name to any type structure.
So type is more general purpose?
You could say that. Yeah. An interface, on the other hand, is primarily designed for defining the shape of object types, like objects with properties. And it explicitly supports the extends keyword for object inheritance. which feels very natural if you come from an OOP background.
Okay, so interface is more focused on object shapes and inheritance.
Right. And one key difference, especially relevant for large modular applications, is something called declaration merging.
Declaration merging, what's that?
Imagine you're building a modular application. Maybe different teams contribute to a shared user interface definition. With declaration merging, one team can define interface user_i.string in one file, and another team can define interface user email.string in another file. TypeScript is smart enough to combine these into a single, comprehensive user type definition behind the scenes.
Wow, so they just merge together automatically.
They do. It's like building a shared blueprint piece by piece. This isn't possible with type aliases. You can't declare the same type twice.
So interface offers a unique kind of extensibility, especially for shared definitions across modules or libraries. What's your take then? When should you prefer one over the other? Is there a rule of thumb?
It's nuanced. While for internal code within a single project, personal preference often dictates the choice, and consistency is key.
Right.
For public APIs or libraries that others will consume, interface often becomes the standard choice. Its declaration merging capability allows consumers of your library to seamlessly extend your definitions, perhaps adding custom properties without breaking changes. This makes interface a more robust choice for defining extensible contracts.
So library authors often lean towards interface.
Generally, yes. The TypeScript team itself suggests defaulting to interface and using type only when you specifically need its additional flexibility, like for union types or map types.
Wow.
However, some experts actually recommend the opposite, defaulting to type, because it's generally more flexible overall and perhaps less surprising, precisely because it doesn't have features like declaration merging, which can sometimes be unexpected.
Okay, so differing opinions even among experts.
Absolutely. Ultimately, the difference in most day-to-day coding is small enough that consistency within your team is probably the most important factor. But understanding these distinctions empowers you to make informed architectural choices, especially when designing reusable components or libraries.
Fascinating. So whether you lean towards type or interface, understanding the nuances is definitely key. Now let's move beyond the core concepts and into more practical application and best practices. How does TypeScript truly elevate the developer tooling and the whole experience of writing code?
It's really all about providing an incredibly rich and intelligent development environment. Visual Studio Code, for instance, which is super popular, offers robust TypeScript support out of the box that transforms how you interact with your code.
How so?
You get instant hover information showing type details and any associated documentation, signature help that guides you through function parameters as you type the function call, and built-in code snippets. Most critically, it provides powerful real-time error and warning reporting.
Right there in the editor.
Right there. You get inline errors directly in your code, squiggly lines under problems, and a dedicated problems panel that acts as your comprehensive issue tracker for the whole project.
So immediate contextual feedback without even needing to compile or run the code manually? That's a massive leap in efficiency, surely.
Absolutely. It shortens the feedback loop dramatically. Beyond just error reporting, IDEs offer powerful built-in refactorings. Things like rename symbol, extract function, or extract constant. These leverage TypeScript's deep understanding of your code's types and structure to safely reorganize and improve your codebase. Then, for maintaining consistent code quality and style across teams, linters and formatters like ESLint and Prettier become indispensable allies.
Okay, ESLint and Prettier. How do those integrate with TypeScript? Are there special versions?
Great question. ESLint, the linter, statically analyzes your code to find potential issues beyond just type errors, stylistic problems, potential bugs, anti-patterns. It allows you to define custom lint rules and offers autofix suggestions. There are specific TypeScript plugins for ESLint, like at TypeScript ESLint Tyslint plugin, that add rules which understand TypeScript's syntax and types.
So it's type-aware linting.
Exactly. Prettier, on the other hand, is a widely used opinionated code formatter. It automatically enforces a consistent code style across your project, handling things like indentation, spacing, line breaks, quote, styles. It pretty much eliminates manual formatting debates.
Thank goodness for that.
Right. A common workflow involves setting up package.json scripts like npm run lint to check for issues and npm run format to automatically fix styling with Prettier. For VS Code users, enabling the setting editor.format_on_save.true can automatically run Prettier every time you save a file, providing immediate style consistency.
Nice.
And ESLint, when configured for TypeScript, becomes this incredibly smart guardian for your codebase.
Can you give us a quick example of the kinds of specific problems ESLint helps solve with TypeScript? What kind of rules are we talking about?
Oh, sure. Think of rules like at Typescript ESLint no floating promises.
Yeah.
This one ensures that if a function returns a promise, you actually do something with it, like await it or use dot then or dot catch. You don't just let it float off, potentially causing unhandled rejections.
Yeah, that's a common source of bugs.
Huge source. Or at Typescript ESLint no unused vars. It catches variables that are declared but never actually used, helping keep the code clean. There are rules against using any at Typescript ESLint explicit any, although you can configure it, maybe turn it off if needed for specific cases. There are rules for consistent type imports, naming conventions, tons of them. It effectively acts as a customizable, type-aware guardian, significantly improving code integrity.
That's a lot of control to tailor the experience and ensure robust code. Now, diving even deeper, what are some advanced concepts and best practices that can truly unlock TypeScript's full potential? Where do you go next?
Well, the first, and perhaps most crucial, best practice we already touched on, but it bears repeating.
Yeah.
Try very, very hard to avoid using the any type.
The escape hatch.
The escape hatch, exactly. While it offers immediate convenience, maybe when migrating code or dealing with tricky third-party libraries, using any completely defeats the purpose of TypeScript's static type checking. It essentially opts that part of your code base out of TypeScript's core value proposition, reverting it back to plain old dynamic JavaScript.
Do you lose the safety net?
You lose the safety net in that spot. The goal is always to use specific types or generic types if you need flexibility, or maybe use unknown, which is a safer alternative to any, or to explicitly tell the compiler when a third-party module genuinely lacks types, which we'll talk about.
Okay, so minimize any. What else?
Another critical practice is to enable strict typing in your tsconfig.json. There's usually a strict flag or several related flags like no implicit tanny, strict null checks, strict function types, etc.
Strict null check sounds important.
It is. It forces you to explicitly handle null and undefined values, preventing those common cannot read property of undefined errors. Enabling strict mode activates a suite of these rigorous checks, ensuring your code adheres to TypeScript's highest standards and catches even more subtle potential errors.
So turn strict on. Good advice.
Definitely. Additionally, explicitly writing the return types of functions, especially in strict rule sets or public APIs, is often considered a must.
Even though TypeScript can infer them sometimes.
Even though it often can, yes. Explicit return types make refactoring faster and safer because the function's contract is clear. It significantly aids AI tools trying to understand your code base. And frankly, it just vastly improves code readability for humans too. While type inference is a powerful feature, being explicit can prevent ambiguities and unintended complexities, especially as code evolves.
That makes perfect sense for clarity and maintainability, especially on teams. What about handling external libraries or maybe even parts of your own legacy JavaScript code where TypeScript doesn't automatically know the types? How does it figure that out?
That's where declaration files come in. They usually have a DTS extension. These are the unsung heroes of the entire TypeScript ecosystem.
DTS files.
Yep. The reason TypeScript knows so much about your code, even standard JavaScript objects like math or browser APIs like document, is because it relies on these type declaration files. They contain only type information interfaces, type aliases, function signatures, and no actual JavaScript code. No implementations.
So they're like header files in C++, just the definitions.
That's a great analogy, yeah, exactly. For example, bundled with TypeScript itself are files like lib.ss5.dts, which defines the standard math object, string, array prototypes, all that core JavaScript stuff. And lib.dom.tdes provides all the declarations related to the browser's document object model API window, document, add event listener, etc. These are built-in and implicitly available based on your tsconfig.json settings.
Okay, so TypeScript comes with definitions for the browser in standard JS. But what about all the packages we install from NPM, like React or Lodash or Express?
Right. For external NPM packages, the community relied heavily on a massive collaborative repository called Definitely Typed.
Definitely typed.
Definitely Typed. It hosts thousands of high-quality declaration files written by the community for popular JavaScript libraries. These declaration files are then published to NPM under the @type scope.
I've seen those at types packages.
Exactly. So if you install React, you typically also run npm install savedev at types React. TypeScript's compiler automatically discovers and uses these @types packages to understand the library's API. It's a really elegant system.
It sounds like it. But what if you use some obscure library or maybe some internal company library that doesn't have an @types package? Are you stuck?
Not necessarily. In those rare cases where a module entirely lacks type definitions and you can't easily write them yourself, you can create a simple DTS file, maybe called shims.dts or something, and put this line in it. Declare module, some untyped module.
What does that do?
It basically tells TypeScript, okay, I know about this module named some untyped module. Just treat it as type any for now, and don't complain that you can't find its types. It silences the warnings and lets you use the library, although without type safety for that specific module. It's a last resort, usually.
That's a good safety valve to have, though. Okay, moving beyond specific syntax, how does TypeScript influence broader software design? Does it help with things like design patterns?
Absolutely. TypeScript isn't just about adding colons and types. It fundamentally helps you enforce robust software design patterns through its type system.
How so? Give me an example.
Okay, take the abstract factory pattern. This pattern provides interfaces for creating families of related objects without specifying their concrete classes. In TypeScript, you can define clear interfaces for the factory itself and for the products it creates. Imagine maybe a cloud resource factory interface. It might have methods like create virtual machine and create storage bucket. Different concrete factories, like AWS Factory, Azure Factory, could implement this interface. TypeScript ensures that any factory claiming to be a cloud resource factory actually provides those methods, and that the methods return objects conforming to iVirtualMachine and iStorageBucket interfaces. It makes the pattern explicit and type safe.
So it helps structure your code in more robust and predictable ways by making these patterns concrete in the types. Any other general coding best practices that TypeScript strongly encourages or enables?
Definitely. Defining and enforcing standard naming conventions like, say, camel case for variables and functions and Pascal case for classes, interfaces, and types significantly improves consistency, reduces cognitive overhead when reading code.
Makes sense.
It's also strongly recommended to completely avoid the older var keyword for variable declaration. Use let and const instead. They were introduced in ES6, provide block-scoped variable declarations, unlike var's function scoping, which are generally much less error-prone and easier to reason about.
So let and const over var, always.
Pretty much always. Using access modifiers like private or protected helps limit the visibility of class properties or methods, rigorously promoting encapsulation, hiding implementation details.
Good OOP practice.
Exactly.
Yeah.
And finally, a feature from modern JavaScript itself that works beautifully with TypeScript is destructuring assignment. This lets you easily extract multiple pieces of data from arrays or objects into their own variables. TypeScript ensures this is type-safe, which helps in writing cleaner, more concise code, especially when dealing with complex objects or function parameters.
Nice. Okay, we've talked a lot about theory and best practices. Let's make it really concrete. How does TypeScript actually integrate with the most popular modern web frameworks? You mentioned React, Angular, Vue earlier.
Yeah, it integrates seamlessly, and in many cases, it's now the default or strongly recommended choice. For React, you can easily set up a new project with TypeScript right from the start using tools like Create React App or Vite. Just use the TypeScript template like npx, create React app, my app template, TypeScript.
Okay. And what are the best practices when using TypeScript with React?
Key things involve explicitly typing your component props and state, usually with interfaces or types. So you define interface, user props, name.string, age.number, and use React fkuserprops for your functional component. Rigorously typing event handlers, like knowing an on-click event is a React.mouse event, and correctly typing hooks like useState and useRef to maintain type safety throughout your component logic. Use state string null, for example.
So typing props, state, events, hooks. Got it. And Angular, you said it's the backbone there.
Indeed. TypeScript is the language of Angular development. It's used fundamentally to define components, services, dependency injection, modules, everything. You'll constantly be defining interfaces for structured data, like maybe an interface product, ed.number, name.string, price.number, that you use when fetching data or displaying product details. Angular leverages TypeScript's features like decorators extensively too.
So if you learn Angular, you're learning TypeScript.
Pretty much, yeah. They go hand in hand. For Vue.js, TypeScript also adds crucial type safety, especially to components written using the composition API or script setup. It helps manage component props, emitted events, and complex state management with stores like Pinia. Tools like Vite provide excellent TypeScript support for Vue out of the box, and build plugins like @role plugin TypeScript integrate smoothly, for instance, within configurations like create spic config.
Okay. And backend, no JS.
Yep, backend developers are definitely not left out. You can build incredibly robust, type-safe backend applications using Node.js with TypeScript. Frameworks like Nest.js are built entirely on TypeScript, leveraging decorators and OOP patterns heavily. Even with plain Node.js or Express, adding TypeScript provides huge benefits for maintainability and catching errors early, especially with Node's growing native support for running TypeScript files directly, or via tools like DSNode.
So it seems like TypeScript truly is becoming an industry standard across the entire stack, front-end, back-end, frameworks, tooling.
It really has gained incredible momentum.
Moving into the real world now, how is TypeScript impacting actual projects beyond just the syntax and tooling? And maybe, what does its future look like? Is it still evolving?
Oh, definitely still evolving. But first, impact. TypeScript is incredibly versatile. It supports projects from, foundational learning exercises right up to highly advanced enterprise applications. For those looking to learn hands-on, there are countless great practical project ideas. Build a Pomodoro timer, a weather app using an API, a classic Toto app, maybe a quiz app, or even something more complex like a real-time chat application using WebSockets.
Good learning projects.
Yeah, these projects really help you build practical skills in type safety, thinking about scalable architecture, and integrating with modern frameworks. For advanced users, it powers massive systems like e-commerce stores, complex dashboards, or I've even seen tutorials for building a blockchain explorer with it.
That really demonstrates its breadth, but it goes beyond just traditional web applications too, doesn't it? I've heard about it being used for infrastructure as code, which sounds fascinating.
That's where it truly gets transformational, in my opinion. The AWS Cloud Development Kit, or AWS CDK, is a prime example. It allows you to define your cloud infrastructure, your VMs, databases, networks, serverless functions, using familiar programming languages like TypeScript.
Instead of YAML or JSON templates.
Exactly. Instead of static configuration files, you write code. This code then synthesizes AWS CloudFormation templates behind the scenes for provisioning.
Okay, and what are these constructs I hear about with CDK?
Constructs are the basic building blocks of an AWS CDK application. They're essentially classes. L1 constructs are low-level, direct mappings to CloudFormation resources. L2 constructs are higher-level abstractions, providing sensible defaults and boilerplate reduction for common resources, like an S3 bucket or a VPC. And then you can build L3 constructs, which are powerful, reusable, opinionated patterns combining multiple resources to solve a specific problem, like a complete serverless API setup.
So you're building your entire cloud infrastructure with the same static analysis, type checking, and developer experience benefits that TypeScript brings to your application code. That sounds incredibly powerful for preventing misconfigurations before they ever reach AWS.
Exactly. That's the huge win. Your infrastructure as code definitions benefit from compile time checks, auto-completion, refactoring, all the good stuff. Best practices for IAC with TypeScript include organizing your CDK code for large-scale projects, maybe using multiple stacks, developing reusable patterns like an abstract factory for creating consistent resources across teams, like standardized Lambda functions or S3 buckets with specific tagging and security policies, and creating or extending these constructs. For security, which is paramount with infrastructure, you can use tools like CFNNAG or CDKNAG, and even Checkoff. These tools can integrate with your build process and leverage TypeScript's type information to provide even more precise security and compliance checks before your infrastructure is provisioned.
Catching security issues earlier.
Much earlier. And tools like Amazon Q Developer are even integrating AI-powered security scans and assistance directly within the IDE for CDK code.
And testing that infrastructure must be crucial too, right? How do you test IAC code?
It is. With TypeScript and CDK, you can implement robust testing strategies. Unit tests using frameworks like Jest and TSJest can verify the logic within your custom constructs without deploying anything. CDK also provides tools for snapshot testing, where you assert that the generated CloudFormation template matches a known good snapshot. And you can write integration tests that actually deploy a test stack and verify its behavior.
Wow, testing infrastructure like application code.
Exactly. And for shared constructs, maybe packaged as internal libraries, version control and release management become critical. Using separate repositories, enforcing proper semantic versioning, Semver, and setting up automated CI/CD pipelines for building, testing, and releasing new versions are essential for managing dependencies and enabling seamless upgrades across your organization's projects.
This all paints a picture of a continuously evolving, incredibly robust language and ecosystem, doesn't it? Is TypeScript itself still changing much?
It absolutely does. And yes, TypeScript is an actively developed language. Microsoft and the open source community are constantly working on it. New versions are released regularly with improvements, new features like better control flow analysis, template literal types, etc., and performance optimizations. There have even been significant rewrites to parts of the compiler over the years to make it faster and more efficient. It's definitely not static.
Okay, let's try and unpack all of this then. We've gone from battling those frustrating runtime errors in JavaScript to building large-scale maintainable applications and even defining complex cloud infrastructure using TypeScript. It might have initially presented a steep learning curve, maybe break some brains, like we said, introducing static types and new concepts. But by fundamentally shifting error detection from runtime, where it hurts, to compile time, where it's just part of development, it ultimately equips you with genuine superpowers. It makes your code more reliable, more scalable, and maybe, just maybe, genuinely a joy to work with.
I think that's a fair summary. The profound takeaway here, for me at least, is that understanding and using TypeScript isn't just about learning new syntax, the colons, the interfaces. It's about adopting a mindset that prioritizes clarity, predictability, and proactive error detection. It empowers you, the developer, to write code that's not just functional, but truly robust and future-proof.
So thinking about our listeners, what does this all mean for your next project? Maybe the provocative thought to leave you with is this. Consider how embracing strong, explicit typing in your code might not just prevent bugs, but could fundamentally transform your entire approach to problem solving and collaboration, potentially unlocking new possibilities for innovation and long-term success in whatever you're building.